Good morning. We are going to talk about vector analysis part 3. Specifically, we are going to be discussing integrals. So let's start with line integrals. So we could have different types of line integrals. And here we are using an increment in length, which is a vector. So the element that you see here, that is dr, is a vector. So you write that as x dx plus y dy plus z dz. So you could basically, when you look at these integrals, like for example, line integrals, the idea is to get them to as close as possible, or break them down into simpler scalar integrals so that you can perform those integrations easily. So if I have a simple scalar function like phi, for example, we have seen in the last lecture, if I take a volume or a surface and map out temperature at every point, I can assign a number, say temperature at each point for phi of xyz, and then I'm integrating this with respect to a vector dr. And the symbol here c indicates contour, so we are integrating over a contour or a path. Sometimes these paths may be open, sometimes these may be closed. In case these are closed, you often see a circle here, right? But this could mean a closed surface or a closed volume as well. So it's important to look at the symbol that's here. So here we're integrating over a contour. Sometimes this is also written as P for path, right? But these indicate line integrals. Returning to the scalar function, so if I have a scalar function with a vector, for example, if I have simply phi times dx along x, right? Then I can write that as this x is a unit vector. It doesn't change in magnitude or direction, so it's a constant as such. So I can bring this out. So this is equal to x phi dx, right? So if I have a scalar function for which I have to perform the line integral, then I can write that as phi of xyz along dr, which is vector line increment. That would be equal to simply x of phi along dx plus y with phi along dy plus z along phi dz. Now, if you see, each of these integrals are simply scalar integrals, so you can easily compute them. You can do a similar thing for the dot product. So if you have v dot dr, then you essentially get vx dx plus vy dy plus vz dz as the integrand for the dot product, and then you are integrating it along the contour. So in fact, let's see an example of how to do such a contour integral with an example problem. So here we are given the force exerted on a body, which is a vector, and we need to calculate work. So recall from mechanics that work is simply F dot dr. I'm not going to go into the deeper details here. We are focusing on the mathematical aspect here. So to get the total work, we need to integrate dw, and we are going along the path that is given. The contour is given here. We're going along this. So let's call this point A, call this point B, C. So we're going from ABC. So we're doing this over ABC. So then I have this as over ABC F dot dr. And my dr, I have only two dimensions, x and y, so then my dr is simply x dx plus y dy. So then I would get along path ABC, f is negative y along x and positive x along y dot x dx plus y dy. Then I have this equal to minus y dx, right, this term and this term, plus x times dy, right? This is the integral that I'm supposed to perform while I'm going along the path ABC. right? So we notice that when we are going from A to B, we are going from 0, 0 to 1, 0. So the y coordinate is not changing. So for going along AB, this term would be 0 because the y doesn't change. Whereas while going from B to C, the x coordinate doesn't change. So dx is 0. So then I can write this integral, rewrite that as minus y dx, right? This term is not 0 only along A to B, because only along A to B we have a change in x, and that x is changing from 0 to 1. So we have 0 to 1. Plus, then there is the second integral, that is x to dy. So, and that integral is 0 along AB again. It is 0 along AB because dy for A to B is 0. So that's the reason why it is 0. Right. So, and then we are going from B to C. While going from B to C, we are going from 0 to 1. Y is going from 0 to 1. So I have x dy. So the thing to note here is the second term was 0 while going from A to B because dy is 0 for A to B. And similarly, the first term is 0 while going from B to C because dx is 0 while going from B to C. That coordinate is not changing, right? Then now let's look at the first integrand here. We have y dx while going from A to B, and this is going from B to C, right? And here the y is 0, so this entire term is 0. Whereas here going from B to C, x is 1. We're going from 1, 0 to 1, 1. So then I have simply 0 to 1 going from B to C, 1 times dy, which gives me 1. So that's how we can calculate the line integral along this path A to B and B to C. The important thing to note here is that the integrands became 0 along AB or BC because dx or dy is not changing. This, so by looking at the way the path is, uh, you can arrive at what the integral should be. Okay, now let's discuss surface integrals. So surface integrals are similar to line integrals, except here instead of a line element, dr, we have an areal element. So we have an areal element, which is often indicated by either d sigma or dA or dA or sometimes ds. All these mean the same thing. They're simply areal elements, right? But unlike the line element, when it comes to area, that we need to worry about the direction. So if I'm performing a surface integral on a closed surface, then basically I can consider um, outward normal as positive. So if I have a closed surface, let's say this is a closed surface on a sphere, then if I'm standing here, I consider the outward normal as positive. But if you have an open surface, let's say we have a circle, let me change the colors here. So let's say we have a circle in XYZ. Let's put some coordinates here. So we have X, Y, and Z. So if we have that, then we are simply going to be using the right hand rule. So if I go around this way, my right hand fingers curl this way, then the thumb is pointing along the areal vector for an open surface. All right. So these are very similar to these surface integrals are analogous to the line integrals. So you could have two of these vectors, or here instead of a line element like the previous slide, we have an areal element. So let's quickly look at an example here, so that we can understand surface integrals better. And to this end, I am going to use problem number 1.7 in Griffiths. Essentially, what we have to do is we are given a vector field, and this vector field is denoted by 2xz along x and x plus 2 along y, and then we have y times z squared minus 3 along z, and we are supposed to integrate this along a cube. So to draw the cube, let me change the color. So we are going to integrate it along the cube here, and we have this is the z, this is the y-axis, this is the x-axis, and this cube has a length of 2. So this is x is equal to 2, this is y is equal to 2, and that is z is equal to 2. So it has a length of 2, and we have to integrate this along the surface only for 5 faces of this cube. We are going to ignore the bottom face of this cube, and we are going to find out the surface integral along 2 side faces, right? One top face, and the front and the back. Okay, so let's start with the front face. So if I look at the front face, notice that for the front face, that is this, shown in green, the aerial vector is going to be pointing out, because x is constant for this entire face. X is equal to 2, and you can go around this surface by changing y and z, right? So so if we go around by changing y and d, so then the face is pointing towards the front, so the aerial vector is pointing out, and then we can write the aerial element d sigma for the front face as along x-axis, because it's pointing around this, and I change dy and dz, because x is fixed at 2 for the front face. To go over the front face, we are changing y and z only. So if I want to perform the surface integral of v dot d sigma over the 5 faces of this cube, I'm going to perform the integral on each face and then add them up, right? So this is going to be sigma of all the faces, and I'm going to perform on each face what v dot d sigma is for each face, and then we're going to add them up. So let's look at the top face for the front face. For the front face, we have the aerial element as x dy dz. So I have only the x component in the aerial vector for the front face. So from the entire vector field, because this is a dot product here, from the entire vector field for the front face, v dot d sigma will only be vx dy dz, vx dy dz, because the aerial element has only the x component, right? So then I can write the vx component is 2xz, and so I have dy dz here. So x is equal to 2 for the front face. So by substituting that, I get 4. So I get 4 d4z dy dz, and y and z are going from 0 to 2 because it's a cube. So then I have this as, excuse me, so I have this as 4z with y and z going from 0 to 2. Seems to be some problem. The slides are changing themselves. So dy dz. So I'm going from 0 to 2 for y and I'm also going from 0 to 2 for z, right? So then I can perform this integration, 0 to 2 and 0 to 2 for y and z. I have 4z dy dz. So dy simply integrates to give me 0 to 2 dy, and the next term is 0 to 2 4z dz, right? So the first term gives me number 2, and the second term gives me 4z squared by 2 if I integrate it, and I go from 0 to 2, and that gives me, this cancels out, so I get 2. Z squared gives me 4, so that is 2 times 2, 4 times 4, which is 16. And this is only for the front face. So we have done only for the front face. The answer is 16. Similarly, you can do, say, for the top face, right? If I look at the top face, that is this. If I look at the top face, then here z is fixed at 2, right? Z is fixed at 2, and x and y are changing. And if I go around the path this way, right, then my right hand fingers are going around this way, so the thumb is going to point along this direction, right? So we are going around xy, so our aerial element is going to point along z. So if I do for the top face, the aerial vector d sigma for top face would be equal to along z, and z is constant here, z is equal to fixed at 2, so we have only dx and dy, right? So this would be the aerial element for top. So for this v dot d sigma for the top face, I would get only the z component because the aerial element has only z component. So I would have something like, integral v dot d sigma vz, and the aerial element has dx dy, right? So vz there is y times z square minus 3. So I have y times z square minus 3, and I have dx dy, and both dx and dy are also going from 0 to 2, right? So and we know that z is equal to 2 for this entire face because we're looking at the top face here. So z is equal to 2, so I can plug in 2 square, so that is 4 minus 3, it gives me 1. So I essentially have going from 0 to 2, 0 to 2, 4 minus 3 gives me 1. So I have y times dx dy, right? And this is very similar to the previous integrand, and you can evaluate this for example for the top surface. Then we have to evaluate this part. So we have 0 to 2, 0 to 2, y dx dy, right? When you integrate dx here, you get 2, and when you integrate y, you get y squared by 2, and the limits of integration are 0 to 2, so I get 2 by 2 divided by half and 4 minus 0. So for the top face, we would get the answer to be 4. Similarly, you can do for the side faces, right? And you can see what the answer should be, right? You can repeat like how we did, and that's how you can get the answer for surface integrals. So similarly, we can also have a volume integrals where we are performing instead of over a surface or a line, we are performing integration over over a volume. So here let's do a simple example. Suppose we have a cube here. Now the cube is of length 4, and what we are going to do is we are given that the density here is kz, where k is some constant, and we have to find the mass. So to find the total mass, we integrate dm over the entire volume. So then we have dm is equal to rho dv, right, over the entire volume, and our density is given by kz, so we're going to do kz over the entire volume, right. So when we say kz along the entire volume, what we mean here is that we have dx, dy, dz, all three, right. So we have dx, dy, and dz. So then this is simple enough to perform because all the coordinates x, y, and z go from 0 to 4 for the cube. So then we have three integrals for x, y, and z, and each of these go from 0 to 4, right? 0 to 4 and 0 to 4. And here we have kz, and k is a constant. And so essentially, we can write this out very easily, right? So if I go with dx, I get for dx I get 4. For dy also I get a 4. And for dz we get z squared by 2, and the limits are from 0 to 4, and we have the constant k up here. So I have k, 4 times 4 is 16, and z squared by 4 gives you 16 minus 0 by 2, right? So this gives you um, 8 times 16, so that's going to be 128 times k, right, where k is a constant. So this is a simple volume integral, right? You can have more complicated volume integrals. For example, here I'm just going to discuss this, how to set up the integral of a function, right, which is given as the solid ice cream cone. So you have in the bottom you have a cone, right, and then on the top you have a hemisphere, right. So this we want to set up, for example, the integral of a function f of xyz over this solid ice cream cone. So then to do that, we basically it's easy enough to set up, right? So the first thing we need to know is that we know how z is changing. So for the bottom, the cone part, for this cone part, z is as x squared, square root of x squared plus y squared, and for this hemisphere part, we have this. So essentially, in our volume integral, we have three integrals, dx, dy, and dz. For z, we are going from square root of x squared plus y squared to square root of 1 minus x squared minus y squared, because at the bottom we have a cone and at the top we have the hemisphere. So we are using the corresponding equations. Now we have to set the limits for our dx and dy. So how do we do that? So we do that by taking a shadow. So we imagine that there is some light here. Then you get a shadow, right, in the xy plane, and we can use this shadow to set the limits, right. So if you look at the shadow, this shadow is maximized. You can cover all the xy points here, because at this interface, whatever is in the cone, the circle that's at the bottom of the hemisphere and at the top of the cone, they match here. So here what we would have then is we have right at this interface, that's the circle that we want to map out. We have the cone equal the hemisphere. So we have square root of x squared plus y squared equal to 1 minus x squared minus y squared, right? Or this means x squared plus y squared is equal to 1 minus x squared minus y squared, right? Or then I can write this as x squared plus y squared is equal to half. You can see that this is an equation of a circle with radius 1 by root 2. And that's what we are seeing here. So this shadow region is essentially described by x squared plus y squared is equal to half, which is a circle. So going back to our integral, we had already set up the limits on, so we're integrating f of xyz over this volume, and I have dx, dy, dz For dz, I have already set up the limits going from x squared plus y squared to 1 minus x squared minus y squared, because I'm going from the bottom of the cone to top of the hemisphere in an ice cream cone, right? And for the other two, dx and dy, we're looking at the shadow that covers the maximal number of points in our xy plane. So for case of x, if I take this circle and flip it up, right, it would look something like this, right? This being the x-axis, this being the y-axis. So x is going from minus of the radius to positive of the radius, right? And for the circle, the radius is 1 over square root 2. So in terms of x, I can write it as minus 1 over square root 2 to plus square root 1 over 2. And then x would accordingly go from, sorry, y would accordingly go from y square is equal to 1 over 2 minus x square. So y goes from square root of as this. So then for y, we would have, when this is negative minus 1 by root 2, for y, we have the limit minus of square root half minus x squared. And at the top here, we have plus 1 minus half x squared, right? So to set up any volume integral, first you look at one of the coordinates. For example, here we are looking at the z-axis, and we could set up the limits for z-axis easily. For setting up the limits for x and y, we were taking a shadow, and we know that the maximal xy points are covered at the interface of the hemisphere and the cone. And based on that, we projected this onto xy axis. We have taken only two axes. We saw that this is a circle, that interface. So then we set up the limits on xy, right? So you can use this sort of a method to set up integral over any kind of volume. In fact, there will be some homework problems where you will learn to do volume integrals by using a method that I just described here. So this is with vector integration. So we looked at line integrals, surface integrals, and volume integrals. And a last note is that usually we indicate or denote line integrals as C or P, contour or path. So these are line. And then for surface integral, again, we use S. And for volume integrals, we use V. All right, so this is surface and this is volume. So with that, we stop here as far as the integrals are concerned. In the next lecture, what I'm going to do is I'm going to look at divergence and curl again, and then I'm going to use the fundamental definition of divergence. What we have looked at in terms of divergence is only in Cartesian coordinates. We looked at, for example, del dot V as dou by dou x of V plus dou V by dou Z plus dou V by dou Y plus dou V by dou Z, right? So we looked at divergence mainly in XY in XY in Cartesian coordinates. So we got this simple form. But what we are going to do in the next lecture is we are going to set up look at what fundamentally divergence and curl mean. And from there, we will derive two important theorems. We will derive Gauss's theorem, and then we will derive Stokes' theorem, right? And once these theorems are done, we'll look at other coordinate systems, polar coordinate systems, and look at how these line elements or surface elements that are in the integrals, how these elements change when we change to different coordinate systems. That's what we will look at next. And finally, we will introduce direct delta function, and that should sum up our chapter 1. So I'm going to stop here and remind you that homework 1 is due on August 31st. Okay, thank you.